Welcome to the lecture on Advanced Calculus and Numerical Methods. In my previous lecture, I discussed about what is meant by partial differential equation and how to frame the partial differential equations by eliminating arbitrary constants. In this lecture, I am going to discuss briefly about formulation of partial differential equations by eliminating arbitrary functions. So consider z, a function of x and y. So here we can note that this z is an dependent variable and x and y are independent variable, and this z containing a arbitrary function here. So by differentiating z partially with respect to x and y for an approximate number of times, it is possible to eliminate the arbitrary function. So the resulting equation will be our partial differential equations. So it means that to eliminate the arbitrary functions, we have to differentiate the given equation z for some approximate number of times, so to get a partial differential equation here. Suppose if z is containing single arbitrary function, then the possible first derivatives are sufficient to eliminate the arbitrary function. So if z contain only single arbitrary function, means if you differentiate the z equation only one time, it will be enough. So suppose if z is containing two arbitrary functions, then the possible second derivatives are sufficient to eliminate the arbitrary functions. So the same function z will have two or more arbitrary functions, means we have to differentiate the given equation z twice to eliminate the arbitrary functions and to frame the partial differential equations. Example: form the partial differential equations by eliminating arbitrary functions in the following functions. So now the given problem is z is equal to f of x square minus y square. So given z is equal to f of x square minus y square, call it as equation number 1. So since the function z contains single arbitrary functions, so if you differentiate only one time, it will be enough. So I am going to differentiate the equation number 1 with respect to x. So I'll get dou z by dou x will be equal to p, will be equal to differentiating the function f, I will get f dash of x square minus y square, and differentiating x square, I will get 2x. So call it as equation number 2. So now differentiating equation number 1 with respect to y, I will get dou z by dou y, it will be equal to q. Differentiating the function, I will get f dash of x square minus y square, and differentiating minus y square, I will get minus 2y. Call it as equation number 3. So now to eliminate the arbitrary functions, I am going to divide the equation number 2 with equation number 3, that is dividing p with q. So I can cancel the constants 2 and 2 here, this 2, this 2. The function also I can cancel here. So remaining will be, I will get x by minus y. So on taking LCM, I will get minus py is equal to qx, or py plus qx will be equal to 0 is the required partial differential equation. Next problem, z is equal to e power my pi of x minus y. So here this pi of x minus y is an arbitrary function. We need to eliminate that. So given z is equal to e power my pi of x minus y, call it as equation number 1. So if we differentiate this equation with respect to x, so since here e power my is a constant, I can keep e power my as it is. So differentiating z with respect to x, I will get dou z by dou x, it will be equal to p. So e power my into pi dash of x minus y. So on differentiating pi function, I will get pi dash of x minus y. So differentiating x, I will get 1. Again differentiating equation number 1 with respect to y, I will get dou z by dou y. So dou z by dou y will be equal to q. So here we are having two functions in terms of y. So I am going to use product rule here. I am keeping e power my as, I am keeping the function pi of x minus y as it is. Differentiating e power my, I will get m into e power my. Next is plus, keeping e power my as it is, differentiating pi of x minus y, I will get pi dash of x minus y, and differentiating minus 5, I will get minus 1. So only I got negative sign here. Call it as equation number 5. So I can replace this e power my into pi minus xy as z from the equation number 1 and e power my pi dash of x minus y as p from the equation number 2. So if I replace all these values here, I'll get q is equal to mz minus p, or p plus q is equal to mz is the required partial differential equation. So third problem, z is equal to y square plus 2 times of f into 1 by x plus log y. So here the function f of 1 by x plus log y is an arbitrary function we need to eliminate. So given z is equal to y square plus 2 times of f into 1 by x plus log y, call it as equation number 1. So differentiating equation number 1 with respect to x, so z will become dou z by dou x, it will be equal to p. Since y is a constant, it will become 0. Differentiating f function, I will get f dash of 1 by x plus log y, and differentiating 1 by x, I will get minus 2x square, 2 by x square. Call it as equation number 2. Again differentiating equation number 1 with respect to y, I will get q is equal to, q in the sense dou z by dou y will be equal to, differentiating y square I will get 2y. So differentiating the function f, I will get f dash of 1 by x plus log y, and differentiating this log y function I will get 1 by y here. So using equation number 2 and 3 and simplifying it, so I can replace this f dash of 1 by x plus log y as minus px square by 2 in this equation. So if I replace that value here, I got the equation like qy is equal to 2y square minus px square, or px square plus qy is equal to 2y square is the required partial differential equation. One more example, z is equal to e power ax plus by into f of ax minus by. So given problem is z is equal to e power ax plus by f of ax minus by. Call it as equation number 1. So differentiating equation number 1 with respect to x. Since both the terms contain the x variable, we have to use product rule here. So differentiating z with respect to x, I will get dou z by dou x, it will be equal to p. So first I am keeping f of ax minus by as it is. Differentiating e power ax plus by, I will get a into e power ax plus by, plus keeping e power ax plus by as it is. Differentiating f of ax minus by, I will get f dash of ax minus by, and differentiating the inside term ax minus by, I will get a here. Call it as equation number 2. So differentiating equation number 1 with respect to y, I will get dou z by dou y, it is equal to q. So same thing here also, by applying the product rule, I am keeping the function f of ax minus by as it is. Differentiating ax plus by, I will get b times of ax plus by. Again, keeping the function exponential function as it is. Differentiating the function, I will get f dash of ax minus by, and differentiating the inside function, so I'll get minus b here. Call this one as equation number 2. So now to eliminate the arbitrary functions here, I'm going to do some small rearrangement. So what I will do means I'm going to multiply a for equation number 3 and b for equation number 2. I'm going to add it. So I'll get the equation like bp plus aq is equal to a into b e power ax plus by f of ax minus by, plus a into b times of ax plus by f dash of ax minus by, plus ab into e power ax plus by f of ax minus by, minus ab into e power ax plus by f dash of ax minus by. So I can cancel these two equations. Adding this, I will get 2 times of ab into e power ax plus by f of ax minus by, and this complete term is nothing but z from the given equation. So I got the equation like bp plus aq is equal to 2abz is the required partial differential equations. So in the next lecture, I'm going to discuss few more examples on eliminating the arbitrary functions. Thank you.